Slide visible?
Yes, sir.
Okay. So today we'll start neural net. So the basic outline of today's talk is we first we try to understand what is the analogy of neural net with human neural nervous system or kind of human brain. Then we'll see what do you mean by uh, perception. There is two things we try to understand: one single-layer perception and multi-layer perception. Okay. Then we try to understand what are the training algorithm. Okay, this is the training algorithm for a very simple neural network. Mainly, first we start with SLP, and then we try to find out what is the multi-layer perception, what is its advantage, and then its training. Okay, so this is the more or less the outlines of talk of the syllabus. I think this is the topic, which is the last topic before the mid semester. So we will uh, cover up to neural net before mid semester. Okay, fine. So the thing is that first of all we start with artificial neural network that is very much popular with ANN kind of. So what is the basic features of artificial neural network? First of all, it's a neural net. Why it is called neural net? It somewhat mimicking our nervous system network. Okay, so that's why it is called neural net. Some neuronal architecture. This basically is a human neuronal architecture. Or a model, same thing. So it is to some extent it follows the basic principle of this. It is connectionist, so there is a connection, lot of connections. We'll see that how the connections is. Then there is a huge network of parallel distributed processing is involved with this ANN. Neural computation means that it is what I said, a bit similar to the human neuronal architecture, and it's as adaptive to the different human behavior, or you can say the kind of cause effect or kind of human, you can say human action with a particular uh, visual or sensory uh, conditions. So this is the adaptive in that sense. Okay, so the brief history that is long back, 1943, Macula Pitts are generally recognized as the designer of the first neural network. So it's a almost 80 years uh, back. 1949, there is the first learning rule that the algorithm for learning this kind of network. 1969 means Q and puppet perception, perceptive limitation, the death of NN kind of thing. 1980s re-emergence of NN multi-layer perception. So these are the some brief milestones of how artificial neural network is becoming kind of a computational model or evolved as a computational model. Right? Now the question is that what is the why it is called artificial neural net? It is somewhat has a similarity or some similarity with brain learning. So that has been the brain has been extensively studied by scientists, but vast complexity prevents from all but rudimentary understanding. That is the major thing. The main thing, whatever we have said in our the most modern science, brain is still a big a big surprise for us. We really don't know much about the brain because how actually it works. So that is a different aspect. First of the architectural aspect, another is learning aspect. Then there is a memory kind of this aspect, and lot of different psychological, parapsychological, metapsychological uh, phenomena that is beyond of our modern scientific. Everything is not still not very much clear for the human brain and corresponding human cognition. Okay, so we just we can say that in a very naive way, this ANN or this kind of artificial neural network, to some extent, try to follow a very naive neuronal architecture. So even the behavior of individual neuron is extremely complex. So what basically, say, but surprisingly, the if we try to characterize our human brain, you see that there's a huge collection of neurons there. And switching time in 10 to the power minus, so it's a big 10 to the power minus 3 seconds. That has been rate of, you can say, switching. Now, face recognition is almost 0.1 second. So on average, each neuron has several thousand connections. So it's a huge connection. You can see, you can understand that 10 billion neurons, and if it's a several thousand connection of each neuron, how it is complicated. Hundreds of operation per second, high degree of parallel computation, distributed representation, die of frequently, never replaced, and compensated for problems by massive parallelism. So the idea, you'll see later slides also, the normal human neuron, if you take a single out of it, it's a very simple kind of thing. But it's a massive interconnection, highly distributed, okay, and highly parallel computations in that. So the brain is a kind of, from architectural point of view, it's a huge network. So if we try to, in this our kind of modern AI and machine learning, deep learning, whatever, we try to replicate, try to this brain with this machine. The brain is something very good for pattern recognition, association, complexity, noise tolerance kind of thing. Whereas the machine is more this is calculation, precision, logic sense. That will be much higher than the human brain. We don't have that much. We are not that much precise Humans are not precise as compared to the machine. But we can say the subjective or adaptive power, or subjective, you can say, from the subjective applications such as pattern recognition, objective detection, segmentation kind of thing. This human is much still now better than the image. Sorry, the computer or machine. Okay. So the one human architecture uses the single processing because as far our architecture is concerned, we are trying to say about the computer architecture, 10 millions of operations per second that we can be absolute arithmetic precision. These are the machines we have. The brain uses mainly slow, unreliable processor acting in parallel. So from the processor point of view, these processors are much more precise, much more robust, the machine, whatever we have used. But they are not that in number. The brain uses the lot of the slow, unreliable processors, kind of neuron kind of thing, but they are huge in numbers and they act in parallel. Now, this is the important, this is what is the structure of it. As you see that it is a very simplistic, or in kind of say a very primitive diagram of a neuron. Now here, this is a cell, then a cell body or cell, you can say nucleus kind of thing. And there is some sort of two types of can say branches of this cell. One is called action. This is one branches, and another is called a dendron or dendrites. Okay. Now there is another thing is that this synapse. Synapse is basically the interconnection between two neurons. Okay. So these action and dendrons are improper connections that is used for this particular. So you can say it's a very simple architecture, but there is a massive number of you can say interconnections and parallelism is going on there. So a biological neuron has a cell body. As I said, it's a cell body. This is a cell body. And an input, branching input structure that is called, this basically it's a kind of thing. So those are the inputs to this cell body. Cell body, these connections is called dendrite. The input to this, these are inputs to this. And there is an output from that. That is called action. As you say, that is this action, it's my action. Okay. So this is the input, this output to that. So action connected to the dendrites via synapse. So now this is the thing, how a action is basically, this is the action to a particular cell kind of thing. And now this is another kind of thing, that how actually some dendrite is basically, so that this is the output of this and this is some input. Let's say this is the input. So it is, I write wrongly actually. So this is another. So these interconnections, action and interconnections, it's called the synapse. I would put the action connected dendrites by synapses. This is called synapse. This is one cell body, another cell body, and so on. This is massive interconnection. Okay. Electrochemical. So incoming, what is the signals are propagated from the dendritic input to the cell body and down the action other neurons. So ideally, what is happening here? In this case, the inputs are coming to this cell body, and this is the some sort of pulses, electrical pulses, kind of sensory inputs, and those inputs are basically, there is some chemical balancing there. If this inputs is basically change this chemical balance, then it excited. So it release another sensory output. There's an again electrical signal kind of thing. So it's an electrochemical um, transaction kind of thing. So electrochemical signals are being propagated using this kind of signals, some chemical uh, state changes, and again by the virtue of this particular change, it may or may not excited and correspondingly generate the signals to the other nodes. So that is the idea actually. It's a very simple idea that will basically try to kind of uh, mimic in our uh, artificial neuronal architecture. Okay, so it very kind of very simplistic description, but it exactly happened in this way. Yeah? That how actually it is going to happen, it is beyond of scope. That much biological explanation is beyond of our discussion. Now comes an artificial. Now this is the biological neuron as we discussed. These are the cell body, these are the basic the dendrites, and this is the synaptic connection as the action. Now exactly same thing. Let the cell body is saying this is our cell body and this is our artificial neural network. And some dendritic connection inputs are something like this. This is the input. So you can say these are the input. Now, when it is coming to that, we use some weight here. Let's say I1, I2, I3, let's say IK. And this is W1, W2, W3, to WK. So these are the weight are what? You can say the kind of priority. So of this I. It sometimes this input is that not that much prominent or that much um, strong. So accordingly, this WI is basically trying to do. Or sometimes this I1 is very important and accordingly W1. So it depends on the particular application, particular work. Now, what is this? Is a summation. If you say summation means what? Summation means that it, as I say, that in a very, this is I1 W1 plus I2 W2 plus this is the summation. So actually, this particular thing is equivalent to summation is equal to 1 to k I1 II Wi. This is the series summation of this. So that input is going to sum. And now the question is that, again, it is not that the input is going to be outputted, but there is a concept if it somewhat excited and this excitation is larger than a particular threshold. So there is a, we can put a non-linearity kind of thing. Okay, and this depends the output. Now this non-linearity can be well understood using our one of our condition is called sigmoid. Okay, so what is sigmoid? As you know very well, so this is the sigmoid. This is 0. This is 1. This is 0.5. The sigmoidal curve is so this is actually 1 is this. So this is 1. This is 0. Okay, something like that. So you see, if it is a greater than that, this summation is, if you say this summation is equal to S, and then this, if this summation is greater than of 0.5, let's say, then the output is 1, otherwise 0, or you can say that this is very, very close to 0. So there is no output. So it excited them, and that is the output. Okay. So this is the a very, very naive concept, simple architecture, and we generally call the very a simple artificial neural network, and you can say single layer perceptron kind. It's not exactly, but it is more or less similar. Okay. Now, so if a very simplistic formulation, many simple neural like threshold switching units. As you say, this is a kind of switch, a threshold based switch, that if this particular summation is going to greater this S to this I on W1 to 1 to K, if it is greater than some threshold, then switch on is off. So the threshold switching is in that sense. So many weighted interconnection. Now you see there is a weighted interconnections. That means the input are somewhat weighted. Okay, these IIs weighted otherwise. Highly parallel distributed processing, because it is not that a single neuron. That maybe this is one, if it is one neuron, two neuron, three neuron. It's possible that you can get a lot of interconnections. Something like that. Okay. So there is a lot of interconnection. This is, I would say, a very easy or there's a lot of interconnection. And learning by tuning this connection with. Now, important, this thing is a maximum importance. So that is we're going to understand very crucially. So what do you mean by learning of this sort of neural network? So neural network is as in today's machine learning is concerned, neural net is of a very important, because nowadays we are basically using a deep neural network, and this deep neural network has very become very um, visible or prominent over the conventional other machine learning approaches or models, because of its very um, accurate or more prediction power over the conventional methods. And since neural, it is basically a neural net. Ultimate end of the day, it is a deep means these hidden layers, number of hidden layers is more. Now we'll see in the next lectures why next after medicine we'll see that how these deeper networks, the deeper models matters, or how many if the number of hidden layer matter in that sense. Okay, but importantly, what do you mean by learning? So learning, what do you mean by learning of neural network? So learning of neural net. Actually, learning of neural net in a very simplistic way, that knowing the weights. If we know the weights, then that means, and know the weight means there is a basic understanding that weights, what weights we going to. This you can see that there is a lot of weights is associated here, as I discussed earlier. Every input and every input to output connection is somewhat weight is associated. Yeah. So this is I, this is J, so this is WI. Now the question is that every connection there is a weight. Okay, this is I, this is J, so this is I. Now these weights are such that if we put some weight such that we have a supervised setting, that means we have a input vector, let's say a d-dimensional vector. Okay, so that means what? That means Let's say this is very hypothetically 1.2, 1.5, 2.3.1, 2.3, something like dot dot dot. It is 3.9.3. So this is what I0 or I1, I2, I3, I4, dot 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 ID. So there are that many inputs. And then it is the class belongingness, that the class is, let's say, two class problem plus or positive. Okay. Now the thing is that these values inputs, if we put a weight such that this particular output will be the plus, and this is just a one instance. So it is, if it is that m number of training samples, this is only one training sample. Now such m number of training samples are there, and for each training samples, the corresponding class belongings will be accordingly to their training samples. That these training samples, this class belongs, and you have to find out such wij's so that it meets every possible training sample. And if we find some wij's for all these connections, so that this when we put these terms between the corresponding output correctly, then it is called fully trained with these samples. Okay. So ultimate end of the day, knowing the value, weight value, is basically means the learning. Okay. This is very important that we have to understand properly. So appropriate problem domains for neural network learning. The input is high dimensional, discrete, or real value. What I said, that this is the high dimensional thing. Input space is what? If a feature space is high dimensional, means that it is a d dimensional. Yes. So this is a d-dimensional feature space, and this d is maybe high. Let's say it is a 324 dimensional. Okay, just for example. Okay? So 324 dimensional. So different features, 324 features are there. So this number of one single sample has 324 different values. Okay, and you can see that the feature space it is visualizing is impossible. It's only three dimensional. In this way, if you say that there's a 324 dimension, then you can understand that how complicated this. And the output value is always a discrete values. If it's a binary case, it's maybe 0, 1, 1. That means it is a dog versus non-dog. This kind of classification. It's a binary classification, but it may be a different. If it is a just MNIST data set that we have discussed, we'll discuss this. MNIST means it is what this data set, handwritten digit recognition. So that means how many class of this? Definitely there is a 10 class. 0, 1, 2, 9. So these all this digit recognition, because if we say this, what does this mean? It maybe 1, maybe 7 or something like that. So we have to do this. Okay, so this is the, so but the thing is that output is discrete values, or it can be real valued. If it is a discrete values, then it's called classification problem. Or if it is a real value, it's called regression problem, as we see. From a target function is, form of target function is unknown. So that target function is ultimate end of the day. What is even in neural net, we are going to find a decision boundary, and this decision boundary is of a particular function. It may be a linear, it may be non-linear, it may be quadratic, it may be highly ordered polynomial, it may be anything. So that target function is not known to us. Humans do not need to interpret the result. Okay, so we that the idea is that human brain is kind of a black box. It just see and interpret. But here we have some sort of kind of system that we know at least what is the you can say we know this particular what is the architecture of the system. So this is the basic idea of this ANN. Now this is what I said earlier, that more systematically this is called single layer perceptron. So single layer means this is only one layer. Linear threshold unit it is called also. Okay. Now as I say that there is a n number of inputs, and each input is associated with the weights. X1 has W1, X2 W2, Xn W1. And there is another input. This input is generally called bias. Okay. So this is another special kind of input that is called bias. Sometimes people are asking, what is the difference between these inputs and this bias? Now you see, one thing you can say that we see this regression relationship y is equal to mx plus c. This c is somewhat analogical but somewhat similar to this bias. Now we can see that what does this mean?